afternoon, and thank you for being here with us today. It is my great pleasure to welcome you to this event, which is part of the Chancellor's Colloquium Distinguished Speaker Series for 2011-2012. As you know, we have been able to bring wonderful individuals who are sharing with us their ideas or give us information about important issues both in the state, in the nation, and around the world, and then also engage us in a discussion on these issues. And in the process, we learn more about what is happening nationally and internationally. We engage in this discussion, and then we try to bring more context to impact the issues we are facing every day, the issues we are facing on the long term, as we ourselves as a university are trying to find our path moving forward. So our format this evening is not going to be different than what we had in the last few events in this series, but we will start with a lecture, and Dr. Suresh will give us a short discussion, and then we will have our Dean of Engineering, Enrique Lavernia, who is going to come here on next to the podium, and he will engage in a discussion with our speaker, and then also he will facilitate questions and discussion with the audience. So I would like to start by introducing our Dean. Dean Lavernia joined the campus in 2002 as the Dean of the College of Engineering, where he was also promoted to Distinguished Professor in 2007. During his tenure as Dean, the College of Engineering became one of the nation's fastest growing engineering schools. He also served as the UC Davis Provost and Executive Vice Chancellor from January 2009 to December 2010. Dean Lavernia is a fellow of the American Society of Mechanical Engineering and the American Association for the Advancement of Science, as well as the ASME International. In 2011, Dean Lavernia received the Hispanic Engineer National Achievement Award from Great Minds in STEM and the Distinguished Scientist Award from the Society for the Advancement of Chicanos and Native Americans in Science. He's also the recipient of the ASME International 2013 Gold Medal Award and will be presented the ASME 2013 Edward DeMille Campbell Memorial Lectureship in 2013. In fact, he will receive that. You will present that lectureship, I would like to say. And he was the 2005 recipient of the Outstanding Engineering Alumnus Medal from Brown University. So tremendous distinction for Enrique. And I wanted to thank him for participating in the discussion today. So thank you, Enrique, very much. At this time, I also would like to introduce our speaker. I'm very honored to introduce Dr. Subra Suresh. Subra Suresh is a distinguished engineer and professor who was nominated by President Barack Obama and unanimously confirmed by the U.S. Senate as the director of the National Science Foundation in September 2010. As director of the $7 billion independent federal agency, he leads the only government science agency charged with advancing all fields of fundamental science and engineering research and related education. BNSF's programs and initiatives keep the United States at the forefront of science and engineering, empower future generations of scientists and engineers, and foster economic growth and innovation. At this point, I would like to say that almost all scientists and engineers who have been faculty in many universities have had their early grants, if not multiple grants, from NSF. And so the agency, I would say the foundation, has not only supported the work of scientists and engineers, but has really created the foundation for science and engineering in the U.S. Prior to assuming his current post, Subra served as the Dean of the School of Engineering and the Vannevar Bush Professor of Engineering at the Massachusetts Institute of Technology. His experimental and modeling work on the mechanical properties of structural and functional materials, innovations in materials design and characterization, and discoveries of possible connections between cellular nanomechanical processes and human disease states have shaped new fields in the fertile intersections of traditional disciplines. He has co-authored more than 240 journal articles, registered 21 patents, and written 3 widely used material science books. In 2006, Technology Review magazine selected Suresh, Dr. Suresh, as a top 10 researcher whose research will have a significant impact on business, medicine, and culture. His many honors include the 2006 Acta Materialia Gold Medal, the 2007 European Materials Medal, the 2008 Ehringen Medal of the Society of Engineering Science, the 2011 General President's Gold Medal from the Indian National Science Congress, the 2011 Padma Shri Award from the President of India, which is one of the highest civilian honors from the Republic of India, the 2011 Nadai Medal from the American Society of Mechanical Engineers, and the 2012 RF Mel Award from the Minerals, Metals, and Materials Society. So this is really a very long and wonderful list of distinctions. We are so pleased to have Dr. Suresh with us, and I would like to ask him to come forward and speak with us. Thank you.
Thank you, Chancellor Katehi, for your very kind introduction. Good evening, everyone. I'm going to spend about 30 minutes or so talking about some of the issues we face in the National Science Foundation, some of the broader policy issues, constraints, opportunities, challenges, headwinds, many of which should not come as a surprise to this particular audience, but I'm sure there are some data in there that you may find useful and helpful to put this into a broader context. So I broadly call this as science and engineering research in the globalized world. Before I go to the details of my talk, the thing that's on everybody's mind is the budget for science. And I'm going to get it out of the way in my first 2 slides so that we can focus on other topics. So also to put it in the proper context. The 2013 budget request for the National Science Foundation from President Obama to Congress is $7.373 billion. That's $340 million above the budget that has been signed into law by the President for 2012. We are currently in 2012 fiscal year. That represents a 4.8% increase. So one of the things that constantly people ask is, this is a terrible financial situation, and it's a difficult time anywhere, especially in Washington. And given that, how do you justify a budget request? So hopefully during the course of this brief presentation, I'll be able to convince you the need for this budget request, because it represents $7.4 billion of taxpayer money, your money and my money. And how do we spend it, and how do we spend it wisely and usefully, and what does it buy for us? And I will finish with a story related to this, because this is a question that has not been asked for the first time. And there are millions of people without jobs. We have serious national debt, and why should we invest taxpayer money at this time for this purpose? And this question has been asked many times before. But one of the silver linings in this rather thick, dark cloud is the following. The last year, NSF has received bipartisan support. The budget increase that you see here is among the highest for many federal agencies. We were supposed to have a budget doubling path. We are way off of that. It's unrealistic at this point. We are not on a doubling path anymore. But under the present circumstances, it was interesting to watch, especially during the course of the last 8 months, the bipartisan support for NSF. Let me just give you a couple of examples of this. The markup for the 2012 budget from the Senate originally was minus 2.5%, a reduction of 2.5%. In the House, it was 0% or flat. when it was eventually in conference agreed to, the final number was plus 2.5%. And I'm told by longtime Washington observers and inhabitants that this is the first time in the 61-year history of NSF that the final budget number was above both the Senate markup and the House markup. And that has never happened before for NSF. The second thing is, even in this climate, this was the fastest budget enactment in the last 11 years. We had the budget actually on November 18th for a year that began the previous October 1st. And so those are sort of indications that some kind of working together can happen even in this current environment. And let me give you the latest numbers on where we stand for 2013. It's going to be a very long and tortuous road this year. And this is the latest from last week. The House marked up NSF budget as plus 4.3% compared to 2012. The Senate has marked it up at 3.4%, plus 3.4%. And so again, there is the appropriation subcommittees in both chambers. And again, it's going to be a long road, but if it ends up the way it ended up last year, which is a big if at this point, it will not be too different from what the president proposed for NSF. And so we'll see where it goes. So I'll leave you with those numbers and those thoughts. These are the latest numbers for now. Let me go to the beginning of NSF, why NSF began and why NSF became a federal agency. Dr. Katehi mentioned Vannevar Bush. I still hold on leave the Vannevar Bush Professorship at MIT. Dr. Bush was an electrical engineer at MIT. He was also the first dean of engineering at MIT. And he was one of the two co-founders of a company that eventually became Raytheon. In the 1940s, he wrote this report that you see on your right called Science, the Endless Frontiers. And that had a very interesting thesis, which at that time was extremely controversial. When it reached the desk of the then President of the United States, it was rejected, went back to him. And eventually, President Truman signed into law in 1950 and created the National Science Foundation based on this report. And his controversial thesis at that time was the following: innovation is absolutely necessary for the economic prosperity of a country. And innovation necessarily depends on basic research in science and engineering. And basic research in science and engineering is best done at universities and colleges, where creative minds work and young minds are taught and trained. And this should be the birthplace of innovation. And that innovation is then taken up by industry and government and then put into much broader implementation and use. And that was the thesis. And he further added that it is the role of the federal government to support that ecosystem of innovation by funding research to universities and colleges in the country. And that became the National Science Foundation. So the first year budget for the National Science Foundation in 1950, total budget, annual budget, was $212,000. So we've come a long way to about $7.4 billion. Now, before we get carried away by the current NSF budget, I want to put this in context. Americans last year spent about $7 billion on potato chips. So NSF budget finally has reached on par with our expenditure in potato chips. I want to start with the US and the things that have made the US the unquestioned innovation leader for at least the last half a century, perhaps longer, especially since the Second World War. So what is it about the American innovation ecosystem that has made it the leader, the unquestioned leader by anybody's measure? You look at the number of Nobel Prizes given since any time, especially since 1950, innovations that have come about in every pursuit of every field of science and engineering. Just in the last 15 years, from technological devices and innovations that have come out, from the internet all the way to the latest in portable devices, etc. The ideas have come from here. So what has made the US the birthplace of innovation? There are a number of reasons we can give. I'm just going to list a few, and again, none of this is a surprise to you. Especially since the Second World War, but historically in its entire history, the US has been a magnet for scientific talent from all over the world. Many of the people sitting in the audience are examples of this. Chancellor Katehi is a very good example of this. People from all over the world come here because this is the place where you can do, historically, the best science, the best engineering in an open and transparent society that has all the institutions that nurture and foster this and support this. And that has helped immensely. Despite all the problems that all our universities have at the present time, including cuts in funding, federal funding, state funding, rising costs, etc., national debt, etc., no matter whose ranking you believe in internationally, whether it's the Shanghai Jiaotong ranking or the London Times Sunday Supplement ranking, etc., US News and World Report, if you take the top 10 universities in the world by anybody's measure, at least 7 or 8 of them are still American universities. And in fact, countries large and small that are creating new institutions are modeling their institutions still after American universities, despite all the problems that we have. The higher education system, and California is a very good example of this, in the US has evolved through a very interesting process. People at different levels of economic structure within the society can still reach the top of the innovation ecosystem through a variety of channels. We have community colleges that feed into university systems, public and land-grant universities. We have private universities. We have Ivy League schools. We have public-private partnerships. We have models to support, historically state support. Unfortunately, that's diminishing. Local support for community colleges, federal support for education system, plus philanthropic support, endowments of universities that have nurtured creative processes and methods in various universities across the system. And equally, the flexibility for faculty, students, and postdocs to move within this system freely. And that creates a level of competition that's unprecedented. And that keeps everybody honest, and that keeps everybody wanting to attract talent and keep talent the best possible way. There is a lot of discussion, and I'm going to show you some slides. Other countries are increasing at a much faster rate than we are able to invest in research and development at the present time. But I would argue that it's not just the dollars that's invested that's important to foster an innovation ecosystem. It's equally, dollars are very important, they are necessary to create science, but it's not enough. You need to have institutions, process, and infrastructure that not only ensure but continuously maintain scientific ethics, research integrity, respect for intellectual property, and a politically free, politics-free peer review system or merit review system that has been developed in the US by institutions, Department of Defense funding agencies, NIH, NSF, DOE basic science, etc. They're not perfect, they have their own flaws, but they are as good as you can get anywhere in the world. And those kinds of systems are necessary if funding and investment into science is going to reach its full potential. And I would further argue that it's not only important for the National Science Foundation because of our 61-year rich history to help that infrastructure come about all over the world so that science benefits everywhere. It's our leadership role and requirement that we do so because others look up to us. And I'll talk about one activity week after next at NSF, which is geared along those lines. So on that point, I would personally make the following statement. I believe that good science anywhere is good for science everywhere, provided that there is a free and open peer review system, respect for and infrastructure and institutions to ensure scientific ethics, scientific integrity, respect intellectual property, etc. And if we believe in that, I think all of us, including NSF, we fund only American scientists. We don't send money abroad to support foreign scientists. But American scientists and American universities collaborate with foreign scientists, and how do we engage them? So that's a perspective that's increasingly important on a global scale if we were to address global challenges while we try to maintain our leadership, intellectual leadership in science and engineering. Plus, we have unique models for university, industry, national lab interactions in our academic institutions and other institutions. A little bit about NSF. So it started in 1950. Our congressional mandate is to sponsor fundamental research across all fields of science and engineering, including social, behavioral, and economic sciences, and to support research into STEM education, science, technology, engineering, and mathematics education on a large scale. The only thing we don't do is clinical research because that's the domain of the National Institutes of Health. We are a $7.3 billion agency. Our overhead rate is less than 6%. In fact, this year I expect the overhead rate to be about 5%. Try running any organization with a 5% overhead, especially a $7 billion organization. And in fact, in my congressional testimony, I mentioned this year that it's a lean organization. If we cut any more, it'll become anorexic. And unlike other agencies, we don't do any internal research. All the money we receive goes back to the community. So unlike NIH, NASA, NIST, DOE, we don't do any internal research. So all the money we receive goes back 5%, about 5 to 6%, less than 6% goes for overhead. This year, we will support 285,000 individuals in the US and 1,800 institutions. Every university, every college, pretty much every community college, science museums, K through 12 school systems, et cetera, et cetera. Let me give you a few examples of the impact of NSF. Since 1952, we have given 46,500 graduate research fellowships. There are many at UC Davis. In addition to that, we give 40,000 research assistantships through NSF funding per year. So the 46,500 is aggregate since 1952. We give about 500 to 600 per year, and the 40,000 research assistants per year. Since 1950, 197 Nobel Prize winners have had their prize-winning discoveries tied to NSF funding, 200 of them. So recently I had an opportunity to meet with the King of Sweden just a few weeks before the Nobel Prize ceremony. And we were joking during a cocktail hour that NSF actually has a bigger responsibility and role in the Nobel Prize ceremony because we have to identify the Nobel Prize winners decades before the Nobel Committee identifies them. Actually, we give them more money from NSF for their research than the Nobel Prize gives them when they win the prize. In fact, last year in 2011, 7 of the Nobel Prize winners had NSF funding attached to them. Another metric, of the 46,500 graduate research fellows, 440 of them, about 1%, are members of the National Academy of Sciences. The average for the scientific community is less than 1 in 2,000 or 3,000. So the hit rate at NSF is order of magnitude larger than in the general scientific community. 30 NSF-funded graduate research fellows alone have won the Nobel Prize, including Secretary Chu, as an example. Carl Wyman, who won the Nobel Prize for cold atoms, etc. The social and economic impacts are staggering. So let me give you a few examples. NSF is the only federal agency that takes a long-term view at a time when our attention span is very small. And understandably, we ask the right questions. Do federal dollars lead to economic value? Do they create jobs? That's a very important question. But NSF has to take a long-term view because in science, jobs are created not tomorrow, not next year, but maybe 10 years from now, 20 years from now. And the economic value is also long-term. Here are some examples of this. In the 1960s, when DARPA started supporting GPS, primarily for defense applications, NSF funded basic mathematics, and before formally there was a computer science department in most universities, research into computer science. Who would have thought in the 1960s that GPS will be used by all of us in our portable devices to get home after a meeting or after dinner? Nobody would have thought of it. If we had asked that question, if we had made that a criterion for funding, we would not have funded this. In the 1970s, American industry decided that mathematical and process modeling was an academic exercise, so industry should not be funding. NSF funded it. That led to rapid prototyping, and rapid prototyping played a huge role in our international competition in manufacturing in the 1980s, especially when there was significant competition with Japan. More recently, in 1995, NSF funded 2 young graduate students, a little north of here in California, to do purely mathematics research that at that time had no known practical application. The 2 students are Sergey Brin and Larry Page, who subsequently founded Google, not because of NSF funding alone, but NSF-funded research played a key role in the technology for which they got venture capital funding. Qualcomm got $25,000 when Irving Jacobs moved to California from NSF. Now they employ 21,000 people. Symantec got a $25,000 SBIR grant from NSF. Now they employ 18,000 people. In 1999, President Clinton was at Caltech to launch the National Nanotechnology Initiative. So NSF was the first agency to fund major nanoscience and nanoengineering centers purely for basic research. They did not fund them to create jobs. They did not fund them for economic value. Now I have the data after 12 years. In the last 12 years, NSF funded nanoscience and nanoengineering centers alone, which were funded purely for basic research, have created 180 companies that involve 1,200 major corporations, and they've created tens of thousands of jobs. That's the benefit of basic research. From recent example, from distant example. So what do we do with universities and colleges? Last year, the most recent year for which we have data, 2008, complete data for all federal agencies, 81% of all the computer science research at American universities and colleges, 81% was funded by NSF. In biology, when you exclude NIH, it's 67%. In mathematics, it's 64%. Social sciences, 61%, etc. Engineering average is 39%. And all fields of science and engineering, it's 22%. There are fields, it puts a lot of pressure on us. There are fields, if NSF doesn't fund, university departments will close and fields will disappear once and for all. So at a time of small budget increase or flat budget, when we have to, in a zero-sum game, it puts enormous pressure on us. We cannot close things, because if we close it because of next year's budget, 10 years from now, there will be no intellectual discipline in that field. And that's something we have to take a long-term view. Going from national to global, here are some thoughts. If you look at the global research expenditure for the most recent year, in US dollars adjusted for purchasing power parity, the total research expenditure is 1.4 trillion US dollars, PPP dollars. Third of that is in North America, primarily in the US. Little less than a third is in Europe. About a third, but increasing significantly, is in Asia. And that's increasing very, very fast. And last year, for the very first time, the top 10 countries in Asia invested as much in R&D together as the US did. It has never happened before. Here is a chart. It's a little busy, but you don't have to worry, but I'll just describe the axes. On the horizontal axis, you have investment in R&D as a fraction of GDP. In the vertical axis, you have number of scientists and engineers per million population in different countries. The size of the circle tells you how powerful they are in this space. So all the blue lines, the blue circles, are the Americas. So the biggest blue circle is the US, somewhere to the northeast of the center. All the green ones are Asia. All the orange or red ones are Europe. So if you add this, areas of all the circles, Asia will now surpass the US collectively in terms of R&D investments, and Europe is very close to us. And in fact, they have ambitious plans to surpass us. So I want to point out, I don't want to put too much emphasis on dollars itself. I mentioned the institutions are important and other factors are important, but the people who are also investing are trying very hard to set up those institutions. They may not get there tomorrow, but they may get there a decade from now. Here is another way to look at the same figure for many different countries. So on the horizontal axis, you have number of FTEs of researchers per million inhabitants. So I switch the axis now. Vertical is the percent as a fraction of GDP. And the yellow dot is the US. You want to be in the top right, where you invest a lot of money and you have a lot of human capital to do the research for you. And the countries that are there are Finland, Sweden, etc. In fact, Israel is not on this plot, but it's also there. The US is in a comfortable position, but again, the competition is increasing significantly. So going from good news to bad news, here are some trends. If you take the three major regions of the world, Asia, European Union, and North America, primarily the US, the fraction of college graduates who receive an undergraduate degree in science and engineering. In Asia, about 20% of all the college graduates get their degree in engineering, about 14% in natural sciences. In Europe, it's about 12% for both. In the US, about 11% get their degree, of all college graduates get their degree in natural sciences, only 4.4% in engineering. And we were never very good. So even a decade ago, we were only 7%, but we've been declining. So you can ask the question, if we were never that good, that high as other countries, how did we remain the innovation leader for the last 50 years? That's a very good question. And one of the reasons is that we've been a magnet for talent from all over the world. And in American universities and colleges, in NSF-funded research, NIH-funded research, etc., we were able to attract talent from all over the world. So I know the numbers from MIT. I don't know the numbers here. In the School of Engineering at MIT, there are 375 professors. 43% of them are foreign-born. Pretty much most of them, almost all of them, have their first degree abroad. That means some other taxpayer is paying to train scientists who become part and parcel of the American scientific enterprise. If you look at it that way, it's a significant additional investment in science and engineering. If we lose that, we will lose the leadership. So that's one of the points we want to keep in mind. Yet another very sobering thought. Only 1.43% of all the college graduates in the US are women engineers. Only 1.43%, half the population. And this is something, unless we fix this, and I know President Chuck West from the National Academy of Engineering was here, this is something that he is very worried about and has been talking about it, and we've been having conversations with them about measures to address this issue. I mentioned about annual investments in R&D growth, and here are some examples of this. Between 1996 and 2007, China invested per year 22% more than the previous year during an 11-year period. Malaysia, 18%, Thailand, 14.5%. The only country below the US was 6%. The only country below us was Japan. And there is argument that Japan's innovation ecosystem is actually contracting. So even the European Union was above the US. But we had a significant advantage. We started at a very high level. So we still have a lead. It's not too late to fix this. We still have a lead. But I think this is the headwinds that we are facing at the present time. I don't want this to be a gloomy talk. So I want to focus on some exciting possibilities. If you ask me the question, what is exciting about what NSF does at this point? So NSF does every field of science and engineering. I can describe it in many, many different ways. I'm going to take a very simplified view, and I'm going to capture the excitement of science and excitement of NSF-funded science into two broad categories. So on the one hand, we fund research into neutrino physics, black holes, outer edges of the solar system, distances that are measured in billions of light years, the mega, the giga, the really huge stuff. We can also go to the Antarctic ice, drill 2 kilometers deep, look at the age of the universe, carbon sequestration, fish population, penguin population, interesting data experiments, etc. At the other extreme, we can go to the nano, the pico, the femto, look at things really small and tiny. We can take a single DNA molecule and measure the force on it to a force resolution of a piconewton. So pico is 10 to the minus 12, 1 trillionth of the weight of an apple on your hand when you're standing on Mother Earth. And so you can do all of this. And one of the things you capture is not only the biology of a single molecule in the human brain, but the psychology of the human mind and the coupling between the two. So the neuroscience and cognitive sciences and psychology in new and interesting ways. So this is what I call the new era of observation. We have the tools, technologies, not just the experimental tools, but also the computational simulations, the hardware and software, the theory that goes behind it, and what I call citizen science. So what do I mean by that? An iPad can generate a terabyte of data. So NSF funds telescope facilities in Arizona, in Hawaii, and in Chile. And we are generating many, many terabytes of data per day. So a middle school child anywhere in the world can have access to real-time data that NSF generates. And we can excite that mind and create a pedagogical possibility that did not exist even a few years ago. That's the excitement of science, the new era of observation. This affects every field of science and engineering, including social, behavioral, and economic sciences. Now we go to other exciting broad category, the era of data and communications. And why is this important? The era of observations is creating unprecedented amount of data, plus the citizen access to portable devices and powerful computers like an iPhone generates additional levels of data. But this data, which is increasing exponentially, travels at the speed of light, unvetted, unpeer-reviewed, where facts have the real possibility of becoming facts, or fiction has an equal possibility of becoming fact in a nanosecond or less, and it's difficult to undo it. So from NSF's point of view, what new science do we need so that we can access, archive, retrieve, curate this massive amounts of data and create knowledge out of this and filter useful knowledge out of this while protecting privacy, confidentiality, and interoperability of data when we go from one set of devices to a new set of devices. And how do we do that? What new mathematics needs to be done? Plus we have cybersecurity issues, personal security, confidentiality issues. Then there is the interesting issue related to networking and social sciences. So NSF periodically comes under attack from segments of the population or segments of policymakers that why should you be funding physical sciences with the social sciences with a limited budget while it should be going to only natural sciences. Here is one example of this. One of the earliest funded NSF centers, engineering research centers, is in the state of Oklahoma. This was to predict tornadoes and weather patterns. This center has produced enormous amounts of new knowledge, software that's used all over the world. Our ability and spun off companies employs a lot of people all over the world. And this software has tremendous potential to predict way ahead of time the occurrence of tornadoes. But still, a few months ago, many people died in the state of Oklahoma because of tornadoes. So I asked the director of the center, with all this NSF funding over 25 years, why are people dying still from tornadoes? He said, it's not our inability to predict the occurrence of tornadoes. A greater problem is our inability to predict the behavior of people in response to warnings about tornadoes, which we give ahead of time. So social behavioral research and human behavior is so critical at a time when we are networked. This is why we articulated a new principle and vision for computing at the cutting edge on what NSF will do, and equally what NSF will not do in the next 10 years. I'm just going to finish with a few slides on some of the activities that we have ongoing currently. Our main mission is to support the best ideas and the best people. And another personal conviction that I have is best ideas and best people can happen everywhere. They live everywhere. We just need to find them, we need to identify them, we need to give them an opportunity to support it. This is why NSF supports research in every state in the country. And this is why Congress established the EPSCoR program at NSF. 29 states receive funding through the EPSCoR program, so that because of the notion that good ideas and good people can be anywhere, they may not have the right opportunity to benefit from it. So investing in this is so critical to us. We want to identify individual scholarship, bright ideas, basic research that may not have a commercial potential tomorrow, but that's not the reason for NSF not to fund it. Having said that, individuals alone and even institutions or even one country cannot solve all grand challenges. So how does fundamental research participate in tackling huge problems that an individual cannot address? So we need to also provide facilities for scientists. So there are a number of programs at NSF that not only NSF does, but we partner with other agencies in the federal government and internationally as well. Some of the larger programs: science, engineering, and education for sustainability, sustainability of urban infrastructure, sustainability of planet Earth, sustainability of transportation systems. So these are all examples of this. Cyber infrastructure framework for the 21st century, cybersecurity issues, and personal security of data, portable healthcare, how do we protect confidentiality of that information? National Robotics Initiative. When people think of robots, they think of fun toys. But when we had the Gulf oil spill, without robots and without NSF-funded basic research into robotics, the oil spill would not have been contained the way it was. And I think that's one link. The big chunk of our robotics initiative currently is human-machine interactions, and one of the biggest beneficiaries of that is robotic surgery. So even though NSF doesn't do clinical work, we feed into that. We partner in this with NASA as well. Robots in space is another area. National Nanotechnology Initiative, I already mentioned that. We invest heavily into that. Biomaps, the intersection of biology with mathematical and physical sciences and engineering. Advanced Manufacturing Initiative, where NSF funds in a number of different ways. We fund $65 million a year into a program called ATE, Advanced Technological Education, that supports community colleges. We fund another $60 million into basic research into manufacturing. Secure smart systems and cybersecurity. Materials Genome Project. Can you go to the periodic table and using databases, computational modeling and simulations at multiple scales, atoms to systems, can you predict properties and functions of materials so that you can bring down the time to the design of a material to actual use of the material in practice by less than half the time it currently takes? So that's the goal of the Materials Genome Project. Computational and data-enabled science and engineering. Real-time networks. We are funding 2 major networks right now. Ocean Observing Initiative, that's to look at the health of our oceans on the Pacific coast and the Atlantic coast. This is a large NSF-funded project, real-time data. The other one is National Ecological Observatory Network, or NEON, which is a continental scale network that will provide real-time data. We have another international network that NSF funds in seismology that involves 80 countries and 140 institutions, where if an earthquake happens in Indonesia, our scientists in the US in every location will get the data within a few seconds, real time. And it's only transmission of that information from the sensors. Let me just close with a few pictures. Even in this economic climate, we are doing major new infrastructure projects. Next March in Chile, NSF, in partnership with the European Union and Asian countries, will open something called ALMA, the Atacama Large Millimeter Array Telescope System. Several $100 billion. 70% of all the astronomy observations are made in Chile. NSF-funded research by American scientists made in Chile last year in physics received 2 Nobel Prizes, just as an example. And this is one of the facilities, new facilities that will officially open next year. On October 15th, I'll be at the National Center for Atmospheric Research, Wyoming Supercomputer Center. The state of Wyoming would put up a new building. NSF helped pay for this supercomputer for atmospheric research. We will open this in the state of Wyoming. It's the first NSF funded center in the entire state of Wyoming. It's an EPSCoR state. This is a plane that's owned by NSF. I don't fly in it. It goes through weather patterns to collect data. This is a research plane, and students and postdocs do experiments in this plane. This is housed in Boulder, Colorado. This is the CERN experiment in particle physics, which is funded in Geneva, which is housed in Geneva, Switzerland. NSF funded research that led to the new discovery on the mass of Higgs boson particles. And even though we don't run the facility, we are an active funder of American scientists who do experiments in this facility, and this is in that facility. Just a few examples of new initiatives that I've launched in the last 8 months. There is a partnership between NSF and USAID. USAID funds developing countries. We fund American scientists. Until last year, they were interacting unbeknownst to each other. So the head of USAID is Dr. Rajiv Shah. He and I got together and we launched this program where we will coordinate the peer review for them because they don't have the mechanism for it. When they fund somebody in a developing country, it'll be coordinated with our funded partner in the US so that they can work together. And it doesn't cost either agency any new money, but the impact of this is substantial. So we launched with 6 projects last year. So far, we have 150 proposals for this year. The second project is the NSF Innovation Core, which was launched last year. Why do we need this? So let me show this with this example, this graph. On the left is basic research. This is what NSF has always done. If you go from left to right towards more applied area, NSF has supported STCs. There are all of this at UC Davis, by the way. I talked to many of the leaders of those today. Science and Technology Centers. GOLI is a university industry partnership. Engineering Research Centers. Accelerating Innovation Research. Partnership for Innovation. Industry University Cooperative Research Centers. And then you have small business innovation research, all of this. So when you go from basic research to small business, there is a lot of things that one does. After small business, you have valley of death, where most of the businesses die. If they are successful, it are picked up and they go on. But before you even start a small business, there is a space which I call the ditch of death, where good ideas that are very good science doesn't become good product or technology. So we launched this innovation core to fund exactly that niche area. In fact, there are examples of innovation core at UC Davis. Another issue for us with respect to workforce development, NSF is very heavily engaged in workforce development, where I mentioned the low numbers of women engineers in the country. What can we do? Here is the latest data from the White House Council on Women and Girls. In 1998, this is college graduates in the US, men and women. More women graduate from college than men do. And that gap is increasing, as you can see, in the last 10 years. But the bottom 3 bars that you see on all the bars are the engineering, computer science, mathematics, physical sciences, and biological sciences. They are still a small fraction of college graduation. And there, the fraction, even though women are coming increasingly into the workforce, they are not staying in the workforce. There are many factors for this, so we decided to address this. In addition to addressing issues related to other underrepresented groups, we launched an NSF Career Life Balance Initiative, where we have the First Lady launched it for NSF at the White House last September. And our goal is the following. Last year, 41% of all the PhDs in science and engineering in the US were women. But only 26% of the PhD level science and engineering workforce. So we set a national goal. It's not up to NSF alone. The national goal we set is in 10 years, we want the fraction of PhD level women STEM workforce to be 41%, which is 50% above where we are today. To reach that goal, we need partnership. So the AAU, the Association of American Universities, and APLU will work together. This summer, we're going to launch, we have a workshop where AAU and APLU will come and talk about some of the pilot projects they are launching so that universities can partner with us on how federal, private, and public university partnership can move the needle further. Increasing leverage from abroad is so critical for us at a time when other countries are putting a lot of money in. So we launched a program called Science Across Virtual Institutes. One example, NSF funds $6 million every year in mathematics research in 7 centers in the US. We asked those centers, if you want to collaborate with partners abroad, where would you collaborate? So they chose partners in Asia. So we asked our counterpart agencies in those countries, we put in $6 million per year. How much will you put in so that our scientists can interact with your scientists? They came back with $20 million a year. That's the power of leverage. We launched another one with Finland in the area of wireless communication. We launched a third one in the area of physics of living systems. And this year we will launch several more to leverage our resources in the US with resources from abroad that benefit American scientists and students, young people. I think this is my last but one slide. We launched a program to foster interdisciplinary research, a program called Inspire. The idea is the following. If you have pre-packaged ideas, we actually steer the community in a different direction. We don't want to do that. We want the community to tell us what unexpected ideas, transformative ideas, perhaps high-risk ideas should be supported. So the way we did this was we will get ideas from the community. You mix any 2 fields you want for transformative research, and we will try to support that centrally without pre-packaging it. So the budget for FY12 for this is $24 million. Our request for 13 is $63 million. So we'll see how this succeeds. The initial signs for proposals is very, very encouraging. So we'll see where this goes. My last slide, I talked about good science anywhere is good for science everywhere if certain criteria are met, like peer review, scientific ethics, scientific integrity, etc. Week after next at NSF, we invited 46 countries, G20 plus OECD countries, NSF counterparts, the heads of agencies will come to NSF. I invited 46 of them. 45 of them are coming at their own expense. And the idea would be we'll be releasing a merit review principles document, which has already been worked on among the 46 countries. What does it do? If you want to be a global player, a global partner in scientific research funding with your own country's taxpayer money, these are the minimum set of principles that we all agree to. Peer review, openness, transparency, confidentiality of reviewers, free of political influence, etc., etc. And we're not signing anything, we don't have an MOU, but there's a principles document. As part of this, we are creating something called the Global Research Council. So funding agencies from all over the world will come together, and they will form an entity that each year will take up an issue like peer review. This year is peer review. Next year it could be IP. Next year it could be ethics or integrity, etc. And we will take this forward. And the goal would be 10 years from now, how can we address major challenges that affect humanity by sharing in funding? Pre-competitive. Of course, we can only fund American scientists. They have their restrictions as well. But while protecting innovation, protecting intellectual property, how do we collaborate? So that's one of the goals of this. So with this, I'll stop. Thank you very much. Thank you.
Well, again, Subra, on behalf of the UC Davis community, we're absolutely delighted and thankful that you're here with us. I can't think of a more critical time in the history of the nation where science and technology is expected to solve so many critical problems. And I guess I'll start with a question and then open it up. And as I listen to your presentation, on one hand, it's absolutely encouraging to see the investments in both infrastructure and resources that the foundation is making, in making sure that the health of this American innovation ecosystem is healthy. You have the metrics. I think it's very impressive. You look at the number of Nobel Prizes, the number of awards that recognize excellence. On the other hand, you see the numbers of students graduating in STEM, 4.5% versus over 20%. It seems to me that's a real threat to the health of that ecosystem. It has been argued that what the nation needs is a definition of a major national grand challenge to unite and inspire young people. We have, and I've often heard our Chancellor talk about what inspired her getting in engineering. It was the landing on the moon. And I'm sure you've run across these stories many times. So the question is, what, if any, role should the foundation have in trying to define a grand challenge for the nation that can truly inspire generations all the way down to K-12?
So I think it's a very, very valid question, and this is something that, as you know well, we have, there are different entities that are defining these grand challenges. The National Academy of Engineering a few years ago came up with 14 grand challenges for the 21st century. I think the difference between the Sputnik era and now is you don't have a single competition that's racing ahead in a single mission. The grand challenges are diffuse, and the competition is diffuse. So China could be, in terms of investments in R&D, in terms of a variety of factors, but we don't have a single grand challenge. I think that's the issue. So there is a lot of conversation in Washington about how to galvanize the scientific community, and especially how to inspire the K through 12 kids that will go into science and engineering. There are a variety of factors, I think, that come in the way of this. And part of the thing is the misunderstanding about science, the misinterpretation of the role of science, etc. But grand challenges are a mechanism that should be sustained. And sometimes one of the interesting things, especially in the NSF is unique in this because we are the only agency we call a non-mission agency. It doesn't mean we don't have a mission. Our mission is not to push a mission. So NASA can push space and aerospace research. DOE pushes energy. Department of Defense pushes a particular technology. We cannot by congressional mandate. NSF cannot say robotics challenge or a sustainability challenge because that's not our mandate to do. So we have to be careful within the space we are allowed to operate in by Congress, what we can do. But having said that, we just released a vision document for computing, which is a huge issue. 81% of our funding in universities for computer science is from NSF. So there we have identified what we call grand challenge communities. And we'll be articulating a grand challenge. So in that space, we are able to do that.
Thank you.
Just one other point on that. Sometimes grand challenges come in ways in which we don't expect. I tell this story often on why should we fund research, and especially in the spirit of something that will shake the world and change the world forever. Maggie Thatcher recently published an autobiography in which she narrates a encounter between the British scientist Michael Faraday, who first produced electricity in the lab, and the then Chancellor of the Exchequer, William Gladstone. So when Faraday first met Gladstone asked him, why should the British government pay for your curiosity to play in the lab to produce electricity? What is the use of your research? To which Faraday responded, sir, one day you will tax it. So that's the argument I give. If you take the $7 billion investment in NSF and the revenue to the US Treasury from that investment, it's many, many times $7 billion. So.
Thank you. So I'd like to open it now for the audience to ask questions. We have microphones on both sides. If you raise your hand, we'll bring the microphone forward. I see a hand over here. Andres?
Hi, I'm Andreas Albrecht, Chair of Physics. So the world's becoming much more globalized, and I really feel that science has always been at the cutting edge of that, and we have a common culture with lots of countries, and we have for many years. And for big projects, it's becoming more and more sensible to actually collaborate on big experiments. But the discussion often becomes very nationalistic. Keep the U.S. in the lead, but bring in international collaborators. People are complicated, and I'm not asking for a fix, but I'd be really curious on your perspective on that tension between between the two?
So I think the tension arises, it's not just for the US. I mean, it's also for other countries. Most of the funding agencies in most countries cannot send money abroad. And it's bilateral or multilateral. So that's why one of the, you're absolutely right. I mean, I've benefited from this in my own research. In fact, when I switch fields, oftentimes it happened because I was able to set up a lab abroad much easier than I was able to set up in my own institution because I had opportunities for funding from, I could do it anywhere in the world. And cutting edge science moves that way. But I think it's also important that, as I said, my direct response to that is good science anywhere will move science everywhere, right? But here are the issues that come in on a day-to-day basis, and especially in Washington. If we have an open and transparent system where we fund taxpayer money, say at UC Davis, you generate data, we put it on the web, and anybody from the world can see it. If somebody in another country doesn't reciprocate, then is it a level playing field? So how do we get there so that everybody operates from the same page of the textbook and same set of guidelines? And that's one of the objectives of the Merit Review Summit. And we cannot dictate to others, this is how we do it, therefore you should do it the way I do it. That'll never work. It never worked. It'll never work in the future. So how do we get there? So one of the things we've done in the Global Merit Review Summit is to invite 46 countries. We would have invited 195 countries. We just don't have the space to do this. We are not the State Department, but we worked with the State Department. This was done at the invitation of the White House. We started with the top 46 countries in the research space. And then we asked them, okay, what is the lowest barrier to successful international collaboration? It's merit review. There is no question about it. If everybody doesn't review the proposals on a common basis, then we have problems. So what we did was we organized regional meetings in 4 different parts of the world. We let them organize the regional meetings. NSF staffed them. That's all we did. We just were observers taking notes so that they didn't go off in different directions. They could invite anybody. So for example, in Asia, Vietnam is not part of G20 or OECD, but they were invited to the meeting. If they wanted to come, Cambodia could come. So anybody could come. Out of this emerged these common principles, which we will release week after next. So this is the way in which we have to take up issue after issue. Our hope is that 10 years down the road, if this experiment is successful, if we can bring everybody not by diktat and my way of doing things, but by building consensus, maybe we can address global challenges in a coordinated way. But still, I don't see how we can go from spending, we cannot fund a scientist in Japan with US taxpayer money, and vice versa. And I think that's going to remain. It's going to remain nationalistic in that sense, but internationally there are tremendous opportunities for us to interact.
Other questions in the back? And then somebody up here near the front.
Hi, I'm Adela La Torre. I'm the Director of Center for Transnational Health. I was really interested in your presentation of the NSF Creative Award mechanism, partly because it seemed very different, but also it was a little more difficult to kind of grasp. What are the key elements that you see, because you're talking about transformational elements and interdisciplinary elements? Could you just discuss it a little more, kind of the overall goals of that and the key elements NSF would be looking at?
Okay. So it's a great question, so I'm happy to answer that. I listed many cross-cutting areas, sustainability, robotics, and things like this. So even though they are sufficiently broad that can include a lot of different fields, one can think of the following possibility. Let's say a young faculty member at some university has an idea that intersects anthropology with computer science in ways in which nobody has thought of. Currently, where would they apply for funding? So there is no formal mechanism to do this. Linguistics and some exotic language and speech recognition, some native Indian language and speech recognition, for example, in computer science. So our goal is that we create a mechanism whereby anybody can propose an idea which doesn't fit into any prepackaged mechanism that we have, which we would fund over a sufficiently long period of time. The mechanism we've set up is half the money comes from a central pool. And let's take an example. There are 3 different fields within NSF, 3 different offices that jointly want to fund a new interdisciplinary idea. It can be one person proposing it. It doesn't have to be multiple people. And that idea, half the money comes centrally. The 3 officers, program officers, divide the other half 3 equal ways. So for 1/6 of the cost, they can leverage it to fund an idea with their existing money, for 1/6 of the money to support it. So the way we decide to do this, at least for a pilot program for the first year, we have 430 program officers at NSF, half of them are from universities. We have people from UC Davis who are IPAs at NSF. And they represent many different fields. So let 3 or 4 of them come together and try to identify ideas from the activities from their communities. And then we have internally a group that's coordinating across the foundation so that the goals are met. So that's where we start with in this process. And as of day before yesterday or so, there were about 100 proposals for this. We'll see how this goes. And this is a pilot for the first year, and we'll fine-tune the process. Everything we do comes from community input. There are a lot of advisory groups, which are university professors, who come and tell us, and that's how all ideas bubbled up. And this was a mechanism that people said NSF needed, and that's why we launched it this year.
We had another question up here in the front.
My question has to do with literacy. I teach English, and for the last 30 years, I've seen, definitely a decline in reading and writing competency of many of our students. Does NSF see this in terms of education in, say, math and science? I mean, are you seeing the effects of this? And if so, are there programs where this is addressed? Again, I'm increasingly seeing my students, unable, for example, to read.
So I would take the view that if somebody is not literate, or they cannot be good scientists, right? So communication is so critical to science in every field of science. I think basic literacy is critical. NSF primarily focuses on research models into STEM. But how do we address this critical issue? So one of the things we did just week before last, we had Secretary of Education Ani Duncan come to NSF, spend 2 hours. So the way the US federal government works, the NSF's role is in STEM education because we are a science foundation. But we fund new models and new research modes into STEM education from K through grave throughout life. But the Department of Education has the mandate to implement it. And they are the ones who deal with the local school systems, school districts, state levels. And so one of the things we started to do this year is have a much greater coordination between Department of Education and NSF. And in fact, I visited Secretary Duncan several times this year, and he came and spent 2 hours with me just 2 weeks ago. And I think it's only through these partnerships that we can do. Another mechanism we have, which we have really accelerated the process, is there is a cabinet-level committee called, as part of the National Science and Technology Council, something called COSTEM, Committee on STEM Education. And that involves 13 federal agencies. Carl Wyman at the White House and I co-chair that. And that committee is now looking into seeing how the 252 STEM programs in the federal agencies can be better coordinated than they are at the present time. So we just released a report that's open on the web on what the 252 programs do from different federal agencies. So those are mechanisms. To your direct question on the literacy part of it, we have to work with other federal agencies. We cannot do it on our own.
So we have time for one last question in the back on the left.
So Joel Friedman, Professor Emeritus in Philosophy. So I'm interested in this difference between the number of engineers we graduate. I think you said 4.5%, whereas in the natural sciences it's 12.
11%.
11, okay. Why is that? Now, I suspect that it has to do with the way engineering is organized into schools. I mean, that's just a hypothesis. But other countries, I imagine, don't have such a differential between natural scientists and engineers. Am I wrong about that? So that's a question. We have to import engineers to make up for this small 4.5%. Have you studied the percentage of graduation in European and Asian countries and try to find out some difference, a reason why there is such a differential?
So there are a variety of reasons for this, but I can give you a few reasons for it, and this is by no means a comprehensive set. If you look at other countries and policymakers in other countries, in Asia, about half of the policymakers, elected officials, government leaders, ministers, have either an engineering degree or a science degree. Europe also, very high number. Take France. École Polytechnique graduates are in the government leadership quite heavily. And that's one difference. So you look at the US policymakers, a very tiny fraction of them are engineers. There are few more scientists than engineers, but still both are very small numbers, relatively speaking. So that's one factor. The second factor, only 40% of all the college freshmen across the country in the US who come to college with every intention of getting a STEM degree, only 40% end up getting a STEM degree, even in 6 years. Right after freshman year, they change to other fields. And there is a perception that STEM, especially engineering degrees, are very difficult and very demanding, and that's a perception. Yet another reason for this, so you take all the standardized test scores in math and science around the PISA tests that are given internationally. The number one country by those metrics is Singapore. 2 is Finland. So if you look at Singapore as an example, why is Singapore so successful in attracting, emphasizing engineering and science in a society? It's a small country. It's much more tightly controlled in terms of its organizational structure because it's very small in a city-state than the US. But nevertheless, why is it? 10% of all the applicants who want to be teachers in schools get selected. 10%. So being a school teacher, K through 12 teacher, is a very prestigious occupation. It's a high-paying occupation, and it's an occupation that attracts the best and the brightest who want to be teachers, school teachers. And one of the problems we have, especially in science, math, and engineering, is attracting the best college graduates to go into teaching at the K through 12 level. And one of the key factors is the low salaries for teachers, and some would argue perhaps lack of enough respect for teachers in society broadly, much more so than it should be. So those are just 3 of the factors that I can list, but there are many more that we can go into.
Well, with that last response, please join me in thanking Dr. Suresh for a fabulous presentation and a great. And please join Dr. Suresh. There's a reception outside, and everyone's welcome. So look forward to seeing everybody out there.